All right, so first, thank you for having me and organizing this workshop. It's very nice organization. So I'm going to talk about Pynapple, which is a Python package we are developing at the Flatiron. First of all, I will talk about what are the issues we are trying to solve. So in fact, the issue we are trying to solve are very similar to the one NWB was trying to solve, or even Datajoint was trying to solve. First of all, we know that experiments in neuroscience are very multimodal, depending on what you record, which tools, which modality. So it generates a lot of different type of files, file structures. And instead, what we want is to be able to compress all those file structures into one particular, a few number of simple universal objects. Okay, so that's one thing we want first, and not having to define all those objects as a function of the experiments. Second of all, many students, when they arrive in the lab, first year, they rewrite the code base from scratch. Sometimes they inherit from some code from other students, and they write their own functions, sometimes very simple functions, such as computing a cross-choreogram. This is a very simple, like traditional analysis in neuroscience, and many people still write from scratch. That kind of wastes some time, so we want a package that provides all those simple functions right away, basically. Then we also know that, as I said, analysis pipeline code is usually not shareable between labs, and even sometimes not within the same lab. So two PhD students within the same lab, one code in Python, one in MATLAB. So it's very hard to basically exchange the analysis. And if you have received like some code from someone for a paper, like if you try to read the code, it's just impossible to read. Or in fact, doing a cross-choreogram, for example, it's something very standard in neuroscience that we should be able to read it from the script. As soon as you see compute cross-choreogram, you know what it is. Okay, you don't need to read the whole function to know that it's correct or not. So like a universal analysis framework, that's what we would like to have. And of course, open source, lightweight, with nice documentation. So 2 years ago, 1 year ago, we released Pynapple for Python neural analysis package. It's on GitHub. It's under active development. It was created first in Adrian Perrache lab, but actually it has a long history. It dates from 20 years ago. There was some people in Bruce McNaughton labs who in MATLAB made the first version called TS Toolbox. Then was TS Toolbox 2. Then there was something called Neuro Series. I inherited Neuro Series, and one thing after the other one, this led to Pynapple, basically. So Pynapple is the most recent version of this approach of data analysis, which is centered around object-oriented programming. So I will define all of this after. So Pynapple is based on Panda. Panda, a very stable library in Python. Like you can't go wrong with Panda. It's very easy to install. Okay. And in Panda, in fact, there are two types of objects that you can use in Panda. The first one is a series, the Panda series. So the series is literally just a column with labeled rows. Okay. So we can use this first object in Panda to derive our first Pynapple object, which is a time series. In neuroscience, many things are organized as a time series. Your LFP, the position of your animal, the calcium transient, a lot of things are time series. So this is our first universal object, okay? The time series derived from Panda. And since it's object-oriented programming, you can basically add some, this is what it looks like. So if you actually install Pynapple and you define your first time series, so for example, here I have 5 time points. This is the data it associates. Very similar to Panda, very easy to read. So since it's object-oriented programming, you can add some methods, some functions to help you maneuver this time series. In this example, here, for example, I'm converting the timestamp from second to millisecond. So again, a set of very well-defined functions that are used every day, 10,000 times a day in your pipeline, but you don't even think about it. But defining them here will help you actually write code with less bugs, because here it has been tested, it's encapsulated in the package, so you don't have to think, oh, is my time point in second, in microsecond, in whatever second, whatever time is do I have? Here it's defined under the hood, so you can forget about it and share your code like this. Other things, such as, for example, restrict to an epoch, binning, time support, I will define all of this after. Second object is a timestamp. Timestamps are very common in neuroscience, spike times, reward times, the time of the production of the stimulus, other things like the moment the animal crosses a particular threshold. Those are the timestamps. So timestamps are also derived from Panda series, and here's one example of a set of timestamps. So as you see on the right, it's none because there is no data, basically. It's just a collection of times. And again, it's object-oriented programming, so you can extend it with multiple functions, as you can see here. So 2 objects so far, 2 universal objects, TSD and TS. We're gonna add 1 more, 2 more. The third one is a data, so it's derived from Panda data frame. Data frame are literally like matrices with label row and label columns. Okay, so from that we can derive another object, which is the interval set. Interval set again are very common in neuroscience, sleep wake, the time the stimulus starts, the time the stimulus ends, and so on. So it looks like this in Pynapple. So if you had, for example, this table with like the presentation of my 2 stimulus start and end, it will appear like this in Pynapple. You type this in your terminal, very easy to read. You understand right away what do you have in your hand, basically. And the nice thing about this approach is that you can use one object to interact with the another one. So in this example, for example, I can use my interval set to restrict my timestamp or my time series. Let's say, for example, this defines the time of the stimulus. I only want the spikes within these 2 epochs. So I can call the function restrict like this. So here I have my timestamp, and if I say ts.restrict ep, I take only the timestamp within the epoch. Okay, super easy to read. You have initiated the code base. You read this ts.restrict ep. Ah yes, okay. Here he's taking the timestamp within this epoch. Okay, very easy to make sense of such code base. You can make other things. For example, so I'm showing you example here. Interval set operation. Let's say you want to merge some 2 epochs. You want to remove some epochs, typically noisy epochs. You want to get rid of them, or you want to intersect 2 good epochs. Let's say, for example, the slow wave sleep during the sleep epoch, for example. So that's interval set. 3 objects. Let's add 1 more, which is a TS group. So TS group, of course, it was made typically for population of neurons. So if you have, for example, 10 neurons recorded together, that's a collection of timestamps. Those neurons, I think someone mentioned this issue yesterday. How do you stack together timestamps who don't have the necessary same times? So here it's inherited from Python dictionary, and it appears like this. So you define, for example, in this example, I have 3 neurons recorded together, 1 from the thalamus, 1 from C1, 1 from cerebellum. And the nice thing about it is I can add some metadata. So those things here are specific to the user. And it will appear like this in Pynapple, where I have my object. I can see right away that I have 3 neurons. I can see their frequency, where they were recorded, and if they have some properties, for example, theta modulation. So this is a collection of timestamps, basically. Again, you can do some nice manipulation. You can take only the neurons you want. You can select. This is typically at the beginning of any of my scripts. I always get rid of my neurons that are below 1 Hz average firing rate. Like I don't want the bad neurons. I just want the neurons that have good firing rate. So I say at the beginning, remove all the ones that are below 1 Hz. And here I have only the neurons above 1 Hz average firing rate. Okay. So again, easy to read if you inherit some code. You can select by threshold, by category, only the neuron in the thalamus, for example. You can select by interval, only the neurons with instant theta modulation. So all those functions are basically part of the TS group object. You can restrict, you can bin. So here, for example, here, I'm binning my spike. So something also that we do all the time. You have your population activity. You want to bin in 1 second, 2 seconds, 10 milliseconds. So instead of having to define those bins yourself and calling histogram, here you can directly do it. You specify the time units, and it gives you the number of spikes per bins here as a nice TSD frame. So basically like a stacked array of TSD. Okay, that clear so far? Okay. So 4 objects, and these 4 objects define the core of Pynapple. Okay, so what we call the core. Those are very stable. The idea that every type of data could be merged almost into these 4 types of objects. of course, it's going to be hard. The only thing that really is super hard to merge into that is movies, typically. Like movies, of course, are, I mean, as Cody, they are like 3D, so it's a bit more complicated. But everything else, like LFP, ROI, anything, you can be part of those 4 objects. If I'm missing something, let me know. But so far, I think it's a good approach. So this is the core. Then one layer above, which we call the I/O, or input-output. So of course, we are targeting system neuroscience. So we show here 3 bubbles that shows basically like electrophysiology, calcium imaging, and behavioral. So the first version of the I/O was very similar to what here the people at Catalyst Neuro have done. The first idea we had is that in our lab, we always have those experiments with like different type of data, and we need to merge them all together in the same global time frame to be able to use them. So the first version, where in this example, for example, I record with Intan, I run kilosort, I record with whatever, I have deep lab cut files. You have to merge all of this together to NWB. That was the first version. I deprecated this version and I moved it to a small package called NWB-matic. And thanks to the work of people at Catalyst Neuro, I suggest you guys use NeuroConf for that. That's I was happy to find NeuroConf actually like a few months ago because I can safely now deprecate my Pynapple I/O. And now I made a new I/O, which I'm gonna explain to you now. So if we use now the tool developed at Catalyst Neuro for making the NWB, one thing we will never get rid of is folders. There will always be folders that you're gonna have to navigate. So if you think, okay, how can I make the user, how can I help the user explore or extract the data from their data set? One of the first things you want is a dataset interface and the NWB interface. So I'm gonna talk about this after. This is work in progress. I'm going to show it about here. This is based on BIDS specification. Like in BIDS, you know, you have it's a folder structure mostly where you have the session, you have the subject, the session, and any derivative. So it's a set of folders. So here, the way to help the user navigate is to basically provide like an easy, like a tree view of that data set, basically. So here, for example, in Pynapple, in just one line, you can load the whole project. And you can call project view and view everything that you have inside your repository, basically. So here you see, for example, I have a bunch of files. So NPZ is the format we choose. You should think of this as, okay, I have my raw data, my origin data. I filter my LFP. I extract something. So for example, the filter LFP is a derivative of my data set. So I want to save that, not as part of the original data set, but as something that I'm going to modify 10 times during the day. So it's not something I should show in the NWB. It's more something that I'm going to extract from the NWB, put it in my session, and this is going to be my derivative, basically. So for example, only those neurons or only this channel. Okay, so small files that can be saved with Pynapple and have this label here to say what type it is. And of course, the NWB file as shown here. And then it's very easy to navigate a project. You can go to, for example, a session. And if I call, for example, in my session, in my folder derivative, give me the spikes, it returns immediately a TS group object. So again, just a nice way to help the user navigate a folder structure. So since it's based on BIDS, I'm just going to show you an example of how to save here. Imagine that I basically define a new TSD here as the sum of my 2 positions, and I define new epochs here. I can save those derivative data inside my folder, my session folder, by just this line here, and I add some description. So the description follows BIDS specification of JSON sidecar. So every NPZ file has a JSON sidecar that can basically hold the description of what it is about, basically. So here you see, give me the information about my epochs, and it tells you the fish pictures to V1, for example. Okay. So maybe more interesting for the people here, I'm going to show you what I've been doing actually in the last 2 days with help from Cody. So NWB interface, you have this NWB file here. So here the idea is that you want to make it as easy as possible for the user to extract the information from the NWB. So I made these things very quickly. It's not in the package yet. But the idea is that if you have an NWB file, you can, in one line, you can load the NWB. and it gives you basically everything inside that is relevant for you. So the metadata, okay, it's important for Dandy, but here I don't want the metadata. I just want the time series and the epoch. That's what I need for Pynapple to take out of it. So what I'm working on right now, and I think I have some issues, so we might need to talk about it after, but give you a nice overview of everything that is transposable from NWB to Pynapple. Okay, so here, for example, I know because I created it, I have all those time series on those two epochs, and if I just do this, it gives me right away my Pynapple object, and then I can start my analysis. That's what I will aim to have in Pynapple as an NWB interface. Okay, we can discuss if it's not a good approach, but I think for the user it's going to be very easy. And I think that's it for the I/O, and I will move to the last part of Pynapple, which is the process. You have taken your NWB, you have extracted the core object. Now what kind of analysis can you do? So here there was a line to draw, because of course you can go very far in analysis in neuroscience, you can implement very crazy things, but the cost of it is the installation, because then you have to install maybe PyTorch, or you have to install some GPU library, and that's very complicated. So it's actually hard to do something simple. People maybe don't realize that, but so we decided to draw some lines of where to go, but the point was not to go too far, basically. And we stopped at 4 different categories of analysis, like once you loaded your data, tuning curve, correction, per-event, and decoding. So I will showcase this with like kind of a toy example. So imagine that you have recorded a mouse moving on a ring here. You record the position of the mouse as an angle. You have a probe here, so you record some spikes. You have some reward. So the data might appear like this, where you have, for example, you have 3 neurons. So those are the spike times of the 3 neurons. There is 2 epochs here, okay? And this is the position of the mouse in the environment, and those are the reward time, okay? This data set, which is a possible data set in neuroscience, will appear like this. So you have the epoch here, you have the spikes as a TS group, the feature as a TSD, and the reward as the timestamps. The first analysis we can do is to compute tuning curve. How many spikes do I observe as a function of my feature is the first question you can ask. So here in Pynapple, it's very easy. It's one line. You give the TS group, you give the feature as a TSD, number of bin, and it gives you the tuning curve for all the neurons. Second thing is, how is my neuron 1 faring as a function of my neuron 2, for example? Oh, sorry, neuron 0 versus neuron 1 here. So here, 0 is the faring of neuron 0. And here is how many spikes you observe of neuron 1 as a function of the spikes of neuron 0. So again, the call of one function is enough, and it gives you for all pairs of neurons this cross-correlogram. Okay, so again, standard analysis in neuroscience. Third, per event, we always want to realign the spike times to a particular timestamp. So here again, the call of one line, the TS group, the timestamps, the windows, and it gives you this TS group actually, which recenters the spike times as a function of the timestamp. So here I'm going to showcase how actually you can stay within Pynapple here, because this for neuron 0 is actually a TS group as well. So every timestamp has been reshifted compared to the timestamp as given as a time of reference. And in fact, this is a different type of thing, but it's still a TS group. So here, this kind of universal object is very handy because it can define a lot of things, basically. And with this TS group, I can then call the count function. So here, I want to generate this figure. I call the count function within this particular bin size. I sum along this dimension, and boom, I have this plot. So here, with just a call of 2 functions, I can generate this very standard figure in neuroscience, the per-event time histogram. Last, decoding. We did a Bayesian decoding. We might implement more. You give so basically, what is my feature as a function of my spikes and my tuning curve? So you give the tuning curve, the spikes, the epoch. And here you can see it decodes only during the epochs. So decoded is in orange. That's the true feature. Okay, that's just an example. So that's the process. So here with the call of 4 functions, I'm able to derive all of those figures from this data set. Okay. Of course, you might think, oh, but in my case, it misses this or that. Over the years, probably this is going to expand a little bit to maybe cover a bit more, especially in the signal processing domain. I'm working on that. So that's Pynapple. We also aim at developing a bit of more tools around it. So the Pynas suite, very quickly, I don't know if am I running out of time? Or 5 minutes, okay. So the Pynas suite will be a collection of tools separated from Pynapple because, again, the goal is to make Pynapple easy to install and very lightweight. So that's why the choice was made to separate the rest. Oh, sorry. We're going to make, I'm working on a GUI for Pynapple. So this GUI is different from maybe NeuroSIF because here my goal is really to make it non-scriptable. Because I think NeuroSIF, you have to script the plot. Here, the idea is that since everything is already set in the global time frame, the idea is to have a GUI where you just have to drag and drop basically every widget. So in this example, you see you have all the Pynapple objects, and you just explore it without scripting anything. Very, very handy for you have acquired your data. It's in Pynapple. You just want to explore quickly your like browsing your data. So that's going to be Pynapception. If, like me, you always forget what analysis you run and you want to keep track of the parameter you choose for your analysis, Pynalog, and that's going to be the Pynas suite. So just so far, Pynapple is on pip, it's installable, it has a limited number of dependencies, so it should not cause any trouble on any machine. Yeah, it has a Twitter account. You can also join this Slack if you want to ask questions or suggest some development. I would like to thank so all those people who contributed to the code base or the documentation. Francesco Battaglia, especially for doing most of the first version, both the TS Toolbox and Neuro series, and those people for contributing to the code base. So the Pynapple is supported by the Flatiron Institute, and if you ask what about more advanced analysis, so we are in the process also of making a package that hopefully is going to depend on Pynapple, that's going to cover like analysis such as, for example, doing a GLM or doing a manifold analysis with your data. So hopefully we're going to be able to release something like a first version soon. And with that, I thank you for your attention.